where is the farthest place you can look with your own eyes? When you gaze upon it, you see not just light, but the collective phantom of 400 billion stars, the breath of a galaxy coasting towards us at a cosmic slingshot speed. This is the universe's biggest, closest, and perhaps most significant neighbor, the Andromeda Galaxy, also known as Messier 31, or simply M31. Tonight, we plunge into that infinite depth, exploring not just a spiral that resembles us, but a giant whispering its own story. A story written across billions of years, leading directly to our own inevitable future. Are you ready to witness the magnificent, terrifying beauty of Andromeda? Andromeda is located approximately 2.53 million light-years from the Milky Way. To grasp this distance, consider that light, the fastest thing in the cosmos, has been traveling from Andromeda to reach your eye since the early Pleistocene epoch, long before modern humans evolved. Yet, despite this immense cosmic gulf, the Andromeda Galaxy is so vast and so close, it remains the most distant object readily visible to the naked eye under a clear, dark sky. The angle it spans in the sky is fully 6 times the width of the full moon. When you look at that faint, misty patch, you are not seeing a cloud of gas, but the combined glow of 1 trillion stars. Andromeda is the undisputed queen of our local galactic neighborhood, the Local Group. This group, a gravitationally bound cluster of over 80 galaxies, includes the Milky Way and the Triangulum Galaxy, M33. However, Andromeda dominates. Her estimated mass is not only greater than the Milky Way's, perhaps 1.5 trillion solar masses compared to our 800 billion, but she hosts a far greater population of stars. While the Milky Way is thought to contain around 200 to 400 billion stars, Andromeda is a titan with an estimated 1 trillion stellar inhabitants. This sheer size is reflected in her structure. Andromeda's stellar disk stretches across a staggering 220,000 light-years, dwarfing the Milky Way's 100,000 light-year diameter. Its spiral arms are tightly wound and feature-rich. Dark dust lanes of interstellar gas, perfect nurseries for future star formation. Like any galactic sovereign, Andromeda is attended by her court, over 30 known satellite galaxies that orbit her immense gravity well. These include the bright elliptical dwarf galaxies M32 and M110, both clearly visible in amateur telescopes. These satellites are not mere companions. They are the unfortunate casualties of gravitational cannibalism. Over billions of years, Andromeda has been stripping away their stars and gas, incorporating their remnants into her own growing halo. This process explains one of Andromeda's most peculiar features: its massive, metal-rich stellar halo, far larger and more complex than the Milky Way's, a testament to her past galactic mergers. At the very heart of this behemoth lies a captivating enigma, a double nucleus designated P1 and P2. When first observed by the Hubble Space Telescope, astronomers were baffled. How could a single majestic galaxy possess 2 distinct peaks of brightness at its core? P1 is the true dynamical center, where the supermassive black hole resides. P2, the secondary peak, is actually a disk of cooler, redder stars that orbits P1 eccentrically. The current leading theory suggests this double feature is the result of Andromeda's gravitational ingestion of a smaller, metal-rich galaxy, perhaps only a few 100 million years ago. The core of that smaller galaxy survived the merger long enough to settle into orbit around Andromeda's own massive central black hole, creating the illusion of a dual core. The central black hole itself is monstrous, estimated to be up to 200 million times the mass of our Sun, a hungry gravitational anchor that shapes the destiny of the entire trillion-star system. Furthermore, Andromeda's central regions are unusually bright in X-rays, a sign of intense activity, perhaps fueled by this complex dual-core structure and the continued accretion of matter onto the supermassive black hole. For centuries, Andromeda was simply known as the Great Andromeda Nebula, a fuzzy patch of light that astronomers assumed was a star-forming cloud within our own Milky Way. This debate over its nature, known as the Great Debate of 1920, was one of the pivotal moments in cosmology. The question was simple yet profound. Was Andromeda an external island universe, a galaxy in its own right, or merely an object belonging to the Milky Way? The answer came in the mid-1920s, thanks to the revolutionary work of Edwin Hubble at the Mount Wilson Observatory. Hubble searched photographic plates of Andromeda and spotted a type of star known as a Cepheid variable. These stars are cosmic yardsticks. They pulsate with a period directly related to their absolute intrinsic brightness. By comparing their observed brightness to their known absolute brightness, Hubble could precisely calculate their distance. The results were astonishing and undeniable. The Cepheids he measured in Andromeda were so incredibly faint that they had to be millions of light years away, far, far outside the estimated size of the Milky Way. Hubble's calculations proved conclusively that the Andromeda Nebula was not a nebula at all, but a separate, massive galaxy in its own right, existing far beyond the confines of our own. This single discovery fundamentally reshaped humanity's understanding of the cosmos, transforming our universe from one contained within the Milky Way to an endless sea of galaxies. This immense structure is not static. It is a cosmic bullet aimed directly at us. Andromeda is hurtling towards the Milky Way at a breathtaking speed of approximately 110 kilometers per second, or nearly 400,000 kilometers per hour. When factoring in the Milky Way's own movement, the combined closing speed is even higher. This collision is not a speculative event. It is a certainty based on the precise measurement of Andromeda's transverse velocity, its side-to-side motion, using the Hubble Space Telescope. The gravitational dance is already underway, dictated by the combined mass of the local group. The two galaxies are destined to merge in approximately 4.5 billion years, an event that has been romantically dubbed the Milkomeda collision. For the stars within both galaxies, the term collision is largely misleading. Because the space between stars is so vast, think of a few grains of sand separated by thousands of kilometers, the chances of two individual stars crashing into each other are incredibly small. Our Sun, for instance, has about a 12% chance of being completely ejected from the resulting galaxy, but only a minimal chance of colliding with a star from Andromeda. Instead, the event will be a graceful, albeit gravitationally violent, intermingling. The two spiral disks will pass through each other multiple times, their massive gravitational fields tearing apart the beautiful spiral structures of both. The process will generate massive shocks, compressing gas clouds and triggering an intense burst of star formation, a cosmic stellar baby boom. After roughly another 2 billion years of chaotic merging, the dust will settle, and a single giant elliptical galaxy will remain, Milkomeda. Our solar system will find itself in a completely new, vast, and perhaps distant elliptical orbit within this newborn cosmic city. Finally, Andromeda is a critical laboratory for studying the greatest mystery of modern astrophysics, dark matter. When astronomers measure the rotational velocity of the stars and gas clouds in Andromeda's outer regions, they find that these objects are moving far too quickly to be held in orbit by the visible mass alone. The rotational curve does not drop off as expected. Instead, it remains high far out into the galactic halo. This glaring discrepancy indicates that Andromeda possesses a massive, invisible gravitational component, the dark matter halo, that completely envelops the galaxy. In fact, the calculations suggest that the overwhelming majority of Andromeda's mass, perhaps 90%, is composed of this mysterious, non-luminous substance that neither emits nor absorbs light. The visible stars, dust, and gas that make up the breathtaking spiral arms are merely a small, visible frosting on an enormous, invisible dark matter cake. Studying Andromeda's rotational curve and gravitational influence on its satellite galaxies provides essential clues to understanding the nature and distribution of this fundamental, yet elusive, cosmic component. It is a constant reminder that what we can see is a tiny fraction of what the universe truly is. Andromeda. She is not just a spiral, she is a mirror of our past and future, hurtling towards us. When we look up at her, we don't just see light. We see the vastness of the universe, the complex history of galactic mergers, the revolutionary power of scientific discovery, the inevitability of change, and the fact that our own galaxy is not alone. We see how we will be reborn in a cosmic embrace 4.5 billion years from now. The next time you gaze into the night sky, look a little longer at that faint light. It is 1 trillion stars and a coming future. That is the infinite depth waiting for you.